welcome to the series on elementary real analysis. In this series, we're going to be exploring the set of real numbers, sequences of real numbers, and practically all of the things you typically learned about the set of real numbers in a foundational math course or single variable calculus course, and probably even past that as well. So where I want to start this series at is just some familiarity with the axioms of the set of real numbers, together with the binary operations addition and multiplication. So we're going to be assuming that the set of real numbers has already been constructed, say from the Zermelo-Fraenkel set theory axioms. But of course, if you want to explore that realm, then a more appropriate venue for that probably would be like a foundational axiomatic set theory series, right? Which, if we haven't done by this time, we'll do sometime in the near future. So let's start off with some of the basic properties that you definitely should know or have experience with the set of real numbers up to this stage. So the first is the closure property of the set of real numbers. So the closure property says the following. The first is that, let's call it 6 point or 1.1. So property 1.1 says that if you take any real numbers x and y and you add them together, you will also get a real number x plus y. And this is going to be for all x, y in the set of real numbers. The second closure property is that if you take any two numbers that are real and you multiply them, their product will also be in the set R. And that again is true for all real numbers x and y. The second property that you definitely know is the associativity property. And it says that if you take x and y and you add them together and then add another real number z, that's actually always going to be equal to x plus the sum of y and z. And again, that's true for all x, y, and z, at least we're going to be assuming so. And the same holds for multiplication. So if you do x times y and then multiply that product by z, you'll get the same answer as if you multiply x by the product of y and z. Right, so that's our associative property. The third property is the existence of identity elements. So the existence of, in particular, unique identity elements. In particular, there exists in the set of real numbers some number 0 such that x plus 0 is equal to x, and this is going to be for all x in the set of reals. And in particular, it's very important to note that 0 also is in this set as well. And also there exists a identity element for multiplication, which we often abbreviate as 1, and x times 1 will be equal to x, and again this is going to be true for all real numbers x, and again it's useful to note that 1 also is a real number. The fourth is the existence of inverse elements. So for addition, this says that if I give you a real number x, there always exists another real number minus x such that x plus minus x is equal to the additive identity element 0. And the same thing goes for multiplication. That is, if I give you a real number x, there always exists a real number 1 divided by x, such that this product is always equal to the multiplicative identity, which is 1. And this is true for all x in the set of real numbers, except for 0. Right? And again, it's very important to note that if x is in the set of real numbers, minus x also will be in the set of reals. And if x is in the set of reals, 1 over x also is in the set of reals as well. Right? So that's the existence of identity elements and inverse elements. The fifth property will be commutativity, or commutativity. And it says that if I give you two real numbers, x and y, x plus y is the same as y plus x. That is, you can change the order. And the same thing goes for multiplication. So x times y is going to be equal to y times x. And so all of these properties practically separate addition and multiplication. The sixth property combines the two into a property called distributivity. And it says that, let's see how do we want to write this, x times y plus z is the same as xy plus xz. And you could also write this in the left fashion, x plus y times z. And usually when we do juxtaposition, we usually imply multiplication. So this is going to be equal to x times z plus y times c. Right? And that is the distributivity property. And a seventh property that we usually take as axiom, if we're not constructing the set of real numbers from the ground up, is the ordering property, which some people also call the trichotomy property. Trichotomy property. And it says that either x is greater than 0, x is less than 0, or x is equal to 0. Right? So we're going to be assuming all of these properties are held. But again, if you want to build the set of real numbers from the ground up from Zermelo-Fraenkel set theory, say via Dedekind cuts is probably a more common way. There are a couple others. One could prove all of these things for the set of real numbers. But again, we're going to be taking these as axioms for this series. The next concept is going to be very useful to us throughout this series on real analysis. Now that we've discussed some of the properties of the real numbers, let us introduce the concept of a metric space. So we say that a set S paired with a function delta, so if somebody says, is S a metric space, that question is not going to make any sense. You need both a set and a function. That function is going to map the Cartesian product of that set with itself to hopefully that set or some other set, but we're going to assume that they're the same in this case, is called a metric space if this function delta satisfies 4 properties. And sometimes it's useful to think of this function as, say, a distance function. So the first property of a metric, that's what this delta is called, is that the distance or the metric of that point with itself is going to be equal to 0. And here x is going to be belonging to S. So the distance from a point to itself is 0. And the distance from a point to another point is always non-negative. Here, x not equal to y, and x, y both belonging to your set S. The third property is that this metric is symmetric. So the distance between x and y and the distance between y and x are going to be viewed as equal. And the fourth property, which is sometimes referred to as the triangle inequality, is usually the hardest one to prove for general sets S and functions delta. And that's the distance between x and y is always going to be less than or equal to the distance between x and z plus the distance between z and y. Right? And again, this property is called the triangle inequality. Right? So those are the 4 properties that need to be satisfied. So for some function delta paired with S, for S delta to be a metric space. So now let's bring this concept into the realm of real analysis. So let's state a theorem and let's prove our first theorem together. And the theorem says the following. Let's define a function between x and y to be equal to the absolute value of x minus y. Then, if we define this function this way, the set of real numbers paired together with this function is indeed a metric space. So we already know that R is a set and it's well defined, at least axiomatically. So all we need to do is show that this function delta satisfies those 4 properties of a metric. And if it does, then we have that R delta is indeed a metric space. All right, so let's prove this. So proof. So the distance between x and x, we need to show that this is equal to 0. So by definition, this is going to be equal to the absolute value of x minus x, which is the absolute value of 0, which we know to be equal to 0. So the first property is definitely met. Now, let's assume that x and y are not equal to each other. So what is the distance between x and y? Is this indeed positive? So the delta, or the distance between x and y, by definition, is the absolute value of x minus y. And we know that this is going to be equal to the square root of x minus y, the quantity squared. So we know that the radical function is always non-negative, and we know that this is going to be equal to 0 only when x is equal to y, but x and y are not going to be equal to each other by assumption. And since that is the property of the radical function, then we have that the second property is indeed met. The third property is that the metric is symmetric, so the distance between x and y and the distance between y and x are indeed equal to each other. So here we're just going to use some magic tricks on the absolute value function. So this is going to be equal to the absolute value of x minus y. And a common trick that's used for differences is we can always factor out a negative sign out of that difference. So we can write that as -1 times y minus x. And we know by properties of absolute values, we can distribute absolute values over products. So we have the absolute value of -1 times the absolute value of y minus x, and we know that the absolute value of -1 is 1. So this is just going to be equal to the absolute value of y minus x, which is by definition the distance between y and x. Therefore, property 3 is met. Now, those three properties are usually the easiest to prove for metric space. It's that fourth that usually takes a little bit of cleverness or tricks or algebra manipulations and so on. Right? So to prove this, we're going to just recall a couple properties from absolute values that you definitely should know in order to follow this proof without any hesitation. The first is that the negative absolute value of x is always less than or equal to x, and that's always less than or equal to the absolute value of x. Another property that you definitely should know is that the absolute value of x squared is equal to the absolute value of x squared, and that's just going to be equal to x squared. And a third property you should know is that if x is less than or equal to y, due to the always increasing property of the square root function, this will imply that the square root of x is less than or equal to the square root of y. Right? Provided that x and y are non-negative integers. Right? So with these little properties of absolute values, let's get it right into this one. So what we're going to do is we're going to begin by taking the absolute value of x, the absolute value of y, their sum, and we're going to square the sum. So what is that? So that's going to be equal to the absolute value of x plus the absolute value of y times the absolute value of x plus the absolute value of y. And then we're just going to use the distributive property of real numbers and see what this comes out to. So this is going to be equal to the absolute value of x times the absolute value of x plus the absolute value of x times the absolute value of y plus the absolute value of y times the absolute value of x, and then the absolute value of y times the absolute value of y. Now, using some of those little properties that I already mentioned before, this is just equal to the absolute value of x, the quantity squared, plus 2 absolute value of x, absolute value of y, plus absolute value of y squared. So, we know that the absolute value of x squared is just x squared, and the absolute value of y squared is just y squared. Now, what is this little 2 absolute value of x, absolute value of y, and what exactly are we going to do with it? So we know that the absolute value of x is greater than or equal to x, and we know that the absolute value of y is always greater than or equal to y. So the product is always also going to satisfy that property. And if you want to have a formal proof of that, it's actually not quite hard. So what we have here is that the absolute value of x plus the absolute value of y squared is greater than or equal to x squared plus 2xy plus y squared, which we know is equal to x plus y, the quantity squared, which we also know is equal to the absolute value of x plus y, the quantity squared. Right? So if we combine these two statements, what exactly do we have? So that means that the absolute value of x plus y squared is less than or equal to the absolute value of x plus the absolute value of y, the quantity squared. Right? So if we take the square root of both of these sides and use that increasing property of square roots, what we have here is the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Now, once you have the triangle inequality established for real numbers, the rest of the proof for this little theorem proof for the metric space of R delta, where delta is the absolute value of x minus y, is actually pretty straightforward. So what we're trying to do is again show that delta xy is less than or equal to delta xz plus delta zy, where x, y, and z are all real numbers. So by definition, we already know that this is going to be the absolute value of x minus y. And what I want to do is I want to introduce z into this picture by adding 0. So this is going to be x minus z plus, or not plus, but minus y. And then I'm going to group my x minus z and my z minus y together because they are just real numbers due to the closure property of R. So if that's the case, that means this must be less than or equal to, by the triangle inequality that we just proved, is going to be less than or equal to the absolute value of x minus z plus the absolute value of z minus y. And we know that that's going to be equal to delta xz plus delta zy by definition. So once we have property 4 established, therefore we have that R delta is a metric space. And again, sometimes it's useful to remind our audience that this delta is not just any metric, but it's the metric delta xy defined to be equal to the absolute value of x minus y, because it's possible that you change this function and our delta is no longer a metric space. So up to this point, we've reviewed some of the important foundational axioms for the set of real numbers, and we've also shown that the set of real numbers, together with the absolute value function, can form a metric space. Throughout the series of real analysis, most of these concepts you've probably already seen, but we need to be very, very comfortable with proving those things based only on our foundational theorems, axioms, lemmas, and so on. So what I want to do now is to explore a couple principles that you've probably used in 1 or 2 previous math courses and see if we can prove these things and show that they are actually indeed true. The first theorem that I want to introduce is the AMGM inequality that you may have used in competition mathematics or possibly even statistics and probability theory. And that's AMGM for arithmetic mean, geometric mean inequality. And from the realm of statistics, at least, this says that the geometric mean gamma is always less than or equal to the population mean mu, and for samples that would be equal to the sample geometric mean is always less than or equal to the sample arithmetic mean. All right, so let's see if we can show this. So the formal statement of the theorem says the following, that the product from k is equal to 1 to m of a series of values to the power of 1 over n, or equivalently the nth root of the product, is always less than or equal to 1 over n times the sum from k is equal to 1 to n of xk. And this is true for xk belonging to the set of non-negative reals and also n belonging to the set of positive naturals. Right? So what I want to do is I want to just prove a special case, and you can see if you can extend this for the general case. So we're going to be proving this for n is equal to 2. Because if you can show it true for 2, then you can probably show it true for 3, true for 4, true for 5, and you can extend that generally if you have the tools for that. Right? So for n is equal to 2, our goal is to show that the square root of ab is less than or equal to 1/2 a plus b. Right? So that's the n is equal to 2 AMGM inequality. Let's break this up into a few cases. I think that's probably an easy way to do it. So case 1. Let's assume that both x and y are both 0. Quite boring, but possible. Right? So if x and y are both equal to 0, then what we have here is the square root of 0 times 0, which we know is 0, and we know that that's less than or equal to 1/2 of 0 plus 0, right? Because that's still equal to 0. So that's obviously true. So case 2, let's make this a little bit more interesting. Let's assume that x and y are both equal to each other, and then both of them are, of course, non-negative. And actually, we can make them strictly positive because we've already assumed the 0 case, right? So if that is the case, or 1 or both equals 0 is practically the same too. So what we have here is the square root of x times y, and we know since x and y are both equal to each other, that's the same as, let's write it as the square root of x times x. X times x, not x times y. So that's going to be equal to, of course, the square root of x squared. And we know that the square root of x squared is just going to be equal to the absolute value of x. And we know the absolute value of x is going to be equal to 1/2 of 2 times the absolute value of x. And we know that that's equal to, again, 1/2 of the absolute value of x plus the absolute value of x. And we know that since x and y are both equal to each other, this is just going to be 1/2 times the absolute value of x plus the absolute value of y. So we have equality for that. And of course, something is always less than or equal to itself, so we can be a little bit more formal and say that that's less than or equal to 1/2 of absolute value of x plus the absolute value of y. So this is indeed true for the x is equal to y case. In case 3, let's assume that they're not equal to each other. Let's assume that x is not equal to y, and let's assume that without loss of generality, x is the larger of the two, because either they're both equal to each other, one is bigger than the other, or vice versa. So, how are we going to prove this one? This is the more trickier one. So if x is not equal to y with x bigger than y, then we know that x minus y is going to be bigger than 0, right? And that's of course true if and only if x is bigger than y. So if x is bigger than y, keep in mind by the increasing property of square roots, that implies that the square root of x is also going to be greater than the square root of y. So you could also say that the square root of x minus the square root of y is also going to be non-negative. So what I want to do is I want to square both sides, so the square root of x minus the square root of y squared will also be greater than 0. Now what I want to do is I want to fill out this left-hand side. So I'm going to have the square root of x squared minus 2 square root of x square root of y plus the square root of y, the quantity squared, and that's going to be positive. And we know that the square root of x squared is going to be x minus 2 square root of xy plus y is going to be greater than 0. And then I'm just going to rearrange this, and I'm going to write this as x plus y is going to be greater than 2 square root of xy. Then I'm going to divide both sides by 2 and reverse my inequality. And what I have is the square root of xy is less than 1/2 x plus y, right? Which is the AMGM inequality, and that completes the proof because those are the only 3 cases. And again, this is true for n is equal to 2, but the proof for n is equal to 3 and higher can inductively be built upon this baseline principle. The next theorem that I want to prove is often used as a proof method in its own right, and that's called the principle of mathematical induction, or the mathematical induction principle. Now, in order to prove the mathematical induction principle, we need to take another theorem or axiom called the well-ordering principle. And the well-ordering principle, or WOP for short, is saying that every non-empty subset of the set of positive naturals always has a least element. And for now, we're going to be taking this as an axiom for the well-ordering principle and using it to prove mathematical induction principle. Now, one could ask, well, do I have to take the well-ordering principle as an axiom? Can you prove the well-ordering principle? We'll revisit this question in the near future, but for now, let's just take it as axiom just to sort of keep things going. So, the mathematical induction principle, what exactly does it say? So it says the following. So what we're going to do is we're going to be letting S be a subset. So if S is a subset, a non-empty subset of natural numbers possessing the properties, the first, 1 is an element of S. So S is a set that has at least 1 in it, so of course it's not empty. And 2, for every k in the set of positive naturals, if k is an element of S, then this is going to imply k plus 1 is an element of S. So if that is the case, so obviously if 1 is an element of S, then that means that 2 is an element of S. If 2 is an element of S, then that's going to imply that 3 is an element of S, and that's going to continue onwards. So if both of these properties are true for this set S, then S and the set of natural positive numbers are exactly equal to each other. right? And in some sense, with that little discussion that I just briefly mentioned, that somehow seems intuitive, right? But let's see if we can give a formal proof for the principle of mathematical induction. So what we're going to do is we're going to prove this by counter example or contradiction, because obviously it's trivial that s and n plus are equal to each other. So if we assume on the contrary, we should be able to easily get a contradiction out of that. So let's assume that s and n are not equal to each other, right? With all the premises satisfied, right? So this has to be true. Let's see if we can make that. So since s is a subset of the natural numbers, and I know it's a subset of the natural numbers because at least one is in that set. So if that is the case, that means if we take the naturals and take away s, that means this is not going to be the empty set, right? So if we take away s out of the set of natural numbers, this is not going to be empty. And why is this the case? This is because we're assuming that s and n are not equal to each other, right? So if s and n are not equal to each other, but s belongs to n, that means there has to exist at least one element x that's in the complement of s with respect to n, right? So that means if you take away s out of n, you should have at least one element there, right? So if that is the case, by the well-ordering principle, there exists an x in the set of natural numbers take away s, such that, that set has a minimum element. So let's assume that this set, ns, has a minimum, and x is that minimum, right? So the well-ordering principle says that the set has a minimum. Let's give the name x, right? And also, it's important to know this is not an element of s, right? So let's see if we can build our contradictions from this. So by property 1, we know that 1 is an element of s, which means that 1 does not belong to n take away s, right? So if 1 does not belong to n take away s, that means that the minimum of n take away s is bigger than 1, right? Because 1 belongs to s. Therefore, the minimum of n take away s cannot be 1, so it has to be bigger than 1, right? And by property 2, if 1 is an element of s, that means 1 plus 1 also is an element of s, which means that 2 does not belong to n take away s, which means that x is bigger than 2, right? The minimum of n greater than s is bigger than 2, right? And I just want to make a quick note here that if the minimum of n take away s is equal to x, and x is greater than 1, then that means x minus 1 will be greater than 0, which means x minus 1 must be belong to the set of natural numbers, because x is not equal to 1, which means 1 minus 1 is greater than 0. That much is guaranteed, right? So with these little observations, let's define a new number. So let us define y to be equal to x minus 1, which we have already established belongs to the set of natural numbers. Again, note that if x is the minimum of n take away s, and x minus 1 obviously is less than x, then that would imply also that y is an element of s as well, right? Because keep in mind, x minus 1, where does x minus 1 belong? Well, x minus 1 belongs to n, that's obvious. But y belongs to s because x is the minimum of n take away s, right? And since 1 belongs to s, that means all numbers from 1 up to the minimum of n take away s belongs to that set by property 2, right? Because if 1 belongs to s, all of its successors will also belong to s, right? And x is the minimum of n take away s, so therefore everyone below that minimum also belongs there, right? Including y. So in some sense, what we're trying to imply here is that y is a maximal element of S, right? So what is the problem with that? Right? So since y is an element of S, we have that y plus 1 is also an element of S, and that's by property 2, right? So that means that y plus 1, which is the same as, well, what is y? Well, y is just x minus 1 by definition plus 1. So what's x minus 1 plus 1? Well, that's just the same as x minus 1 plus 1, because they're just additive inverses, and that's just going to be equal to x. And since y plus 1 is an element of x, that also implies that x is an element of S. But what's the problem with that? Well, before, x belonged to n take away S. It was the minimum of that set in particular. And now we have that x is an element of S. That's a contradiction, because you cannot be in a set and its complement simultaneously. So that's a contradiction, right? So since that's a contradiction, then we have by proof of contradiction that S and N are indeed the same exact set. So now that we have a few proof techniques, for example, of metric spaces, proof by contradictions, let's also do a quick example on mathematical induction on a subset of the reals, just to make sure that our skills are up to par for that. So what I want to do is I want to define a sequence, x1 starting at 1, x2 being 2, and every term thereafter is just going to be the arithmetic average of the preceding two terms. So what our goal presented to us is show that every term in this sequence is always between 1 and 2, right? So it's obvious to show that, 1 is between 1 and 2 is between 1 and 2. And then every average of terms after that, so for example, the next term is going to be 1 plus 2 is 3, and 3 divided by 2 is 1/2. That if I do 1.5 plus 2, and then divide that by 2, I should get a number between 1 and 2, right? At least that's what this theorem is claiming. So if you want to try this proof on your own, feel free to do so. So let's get right into it. So proof. So let's start off with the basic principle of mathematical induction, show that the base case indeed is true, right? So 1 is less than or equal to 1 is less than or equal to 2. So 1, of course, is our target here, and that's, of course, trivially true. So let's do 1 less than or equal to the next term. 2 is less than or equal to 2. So is 2 between 2 and 2? Yes, indeed, that is the case, right? So that's for x1, that's for x2. So that means that if we define S to be the set of all n such that 1 less than or equal to xn less than or equal to 2 is true, then we have that 1 and 2 belong to the set S. So 1, 2 is a subset of S, right? Now let's just, out of curiosity, just check the next term just to see if that's true, because if that's false, then the entire thing is false. So 1 less than or equal to the two terms that precede it, so 1 and 2. So our question is this indeed between 1 and 2? So that's going to be 1 is less than or equal to 1 plus 2 is 3, and 3 divided by 2 is 1.5. And that is indeed between 1 and 2, right? So here we have that x3 is true, which means that 3 also belongs to the set of values that make it true, right? So obviously the base case is met. So now we're going to assume that this is true. So we're going to assume that this is true for, let's assume it's n in the natural numbers, implying that n is an element of S. So if we can show that this assumption implies that m plus 1 is also in the set S, that means S and n are indeed the same exact numbers, right? So since we're assuming that n is in this particular set S, we're assuming that 1 is less than or equal to 1 over xn, 1 is less than or equal to xm, is less than or equal to 2, right? So also, one could show that this is equivalent to also assuming that 1 is less than or equal to xm minus 1. less than or equal to 2. Now, I'll mention briefly once I finish this proof of why this is also true, because there's another theorem that's sort of equivalent to the principle of mathematical induction, right? So 1 is less than or equal to xn is less than or equal to 2. And let's see if we can get anything from this. So if that is true, does this imply that xn plus 1 is between 1 and 2 as well? So by definition, we know that x plus 1 is equal to the average of the preceding two terms, xn and xn minus 1. Right? So this by definition is true. And we just need to show that this is between 1 and 2. Right? So does xn plus 1 belong to 1 and 2? So firstly, we know that xn is bigger than or equal to 1, and we know that xm minus 1 is also bigger than or equal to 1, which means that if we take these two numbers, xn and xn minus 1, that's going to be bigger than or equal to 1 plus 1, which is going to be equal to 2, and I can divide both sides of this inequality by 2, and I have that xm plus 1 is bigger than or equal to 1, because that is indeed the average of those two terms. So we have that xn plus 1 is bigger than or equal to 1. Similarly, we know that xn is less than or equal to 2. We know that xn minus 1 is also less than or equal to 2, which means that xn plus xm minus 1 is going to be less than or equal to 2 plus 2, which is going to be equal to 4. Now what I want to do is I want to divide all sides by 2 so I can generate my average on this right-hand side, and there is xm plus 1, and that's going to be less than or equal to 2, right? So that means that xm plus 1 is less than or equal to 2. And combining these two inequalities in the same exact realm, we have that 1 is less than or equal to xm plus 1 is less than or equal to 2, which means that m plus 1 is an element of S, which means, from the principle of mathematical induction, S and n are indeed the same exact set, which means this inequality is true for all natural numbers n, right? And that completes the proof. Right? Now, sort of what I did there was I implied that, okay, if 1 is there, 2 is there, 3 is there, and that implication step or that assumption step for n belonging to S, practically Sn in all numbers below it are also in S as well. This is what we refer to as the principle of mathematical induction, or the mathematical induction principle variation 2. And it says the following. If the first property, 1, belongs to S, and 2, 1, 2, 3, all the way up to k is a subset of S, if this implies that k plus 1 is also an element of S, some people will change that to k minus 1, and some people will change that to k. They are equivalent. That should be obvious. But if both of these properties are true, then this implies that S and n are indeed the same exact thing, right? And one can also show, and this is practically what allows me to do this little trick in the first place, is that the mathematical induction principle 1 and mathematical induction principle 2 are equivalent, right? So if you can prove one, you can prove the other, and vice versa. You lose nothing or gain nothing from using one over the other, aside from maybe convenience in a particular proof. So those are some of the very foundational things that you should have before exploring the realm of real analysis. There are definitely a lot of fun and exciting theorems and proofs that we'll explore in this series, and I can't wait to see you there. Hope you enjoyed this video, and I'll see you in the next one. Take care.